Hello YouTubers. This video is a small demo on how to create S7 connection between S7-1500 series CPU and S7-1200 series CPU using TCP IP interface. In this example you will find information on configured connection. What is configured connection? Configured connection is connection configured in the hardware configuration of step 7. That type of connection can be used for S7 communication, or open communication with send-receive blocks. As all the communications, doesn't matter what type they are, they need to be initialized, terminated, and in some cases interruption may happen. How does connecting, disconnecting, and interrupting are realized? Connecting is automatic. It means that connection establishment with partner is automatic, and it starts when starting up the communication-capable module. It can be CPU with integrated interface, or communication processor. Operating system of the module assign all the required connection resources on the connection establishment. Disconnecting is not performed. It means that connection is not cancelled after data has been transferred. Connection remains and the connection resources are permanently assigned. They cannot be changed in user program. Interrupting may occur, for example, due to failure. After interruption, operating system automatically re-establishes the connection without intervention of the user. Some resources might be released, so they are reassigned. Next very important topic is data consistency. Data can be consistent or inconsistent. If you create a data area that cannot be changed simultaneously by competing processes, is referred to as consistent data area. Sometimes data area might be larger than the consistent data area, so it can be falsified. The data area can then at a certain time consist of new and partially of old data areas. That might happen while step 7 user program running communication block and it is interrupted by a process alarm OB with higher priority. On this occurrence, there is a possibility that data is changed by user program, while partially has already been processed by the communication block. In this case data becomes inconsistent as a part of it is taken from the time before the process alarm processing, so it is an old data area. And another part of the data is taken from the time after the process alarm processing, so it is new data area. Data consistency is system related or advanced. System-related data consistency is a maximum number of data that is always guaranteed by the operating system of a CPU or communication processor. If the data area is smaller than required in the Step 7 user program, then no any measures in order to guarantee data consistency are required to take into account. Data area will be consistent no matter what. If data consistency is required for a data area larger than consistent data volume, then this can be achieved by additional measures in the Step 7 user program. In this case, the process alarm OB can be blocked for the duration of the data transfer. Let's take a look at the system-related data consistency on the S7-1200 and S7-1500 series CPUs. S7-1200, all elementary data types and system-defined structure. It can be word, double word, IEC timers, and so on. S7-1500, CPU ensures the data consistency for a tag. Advanced consistency. In advanced data consistency case, additional measures must be taken on the sender and receiver sides. On the sender side, access to the send area only after the data was transferred completely. It can be achieved by the help of the parameter done. On the receiver side, access to the receiver only after the data was received completely. It can be achieved by the help of the parameters NDR, new data received. There are two cases that must be distinguished. Client-client communication. Client-server communication. In the client-client communication, if for example communication blocks BSend and BRCV are used, and advanced data consistency needs to be ensured, then the data must not be modified during the transmission. In the client-server communication, if for example communication block put get are used, then system-related size of the consistent data areas must already be considered during the programming or configuration process. In this scenario, step 7 user program of the server does not contain any communication block. Let's try to create a configured communication between S7-1200 series CPU and S7-1500 series CPU. Create a project and insert two stations, S7-1200 and S7-1500. I have already two stations, S7-1513F, 3PNDP, and S7-1214C. Let's take a look at the configuration of the first, S7-1500 series CPU. Select Profinet interface of S7-1500 series CPU. Under the Ethernet address, set the IP address in the IP protocol of your CPU. In interface network, create new subnet. I have left the default name, but you can name it as you fit it comfortable. Switch to the hardware configuration of the S7-1200 series CPU. Under the Ethernet address, set the IP address in the IP protocol of your CPU. IP must be in the same subnet as your S7-1500 CPUs. In the interface network, select already created subnet. Both CPUs are in the same subnet, that enables to create a communication between them. To create a communication, you can use a graphical option. Switch to the network view. Here you can see connection partners, an S7-1500 CPU and an S7-1200 CPU. Now I am going to create S7 connection. As I already mentioned, I am going to do it graphically, as both CPUs are in the same project. By creating S7 connection graphically, the connection is configured on both sides. If you will try to create a connection in network view graphically, you will fail, as connection mode is not active by default. You need to click the connections icon to activate the connection mode. After activating connection mode, possible connection partners are highlighted. In the adjacent drop-down list box, select S7 connection. All devices that are available for an S7 connection remain highlighted. With the button held down, drag the mouse cursor from the interface of the first CPU, where the S7 connection is to start, to the interface of the CPU, where S7 connection is to finish. The start point will be active connection establishment, and end point will be passive connection establishment. As a result, S7 connection configured on both sides is created, and the connection path is displayed highlighted in graphical area of the network view. S7 connection is automatically entered in the connections table. There are two connections created, as S7 connection is configured on both sides. Click on the first row, where local endpoint is S7-1500 CPU. In General tab, select Special Connection Properties. Here you can see that this endpoint sets up the S7 connection actively. Name it as S7 Active Connection. Click on the second row, where local endpoint is S7-1200 CPU. In General tab, select Special Connection Properties. Here you can see that this endpoint participates passively in establishing the connection. Name it as S7 Passive Connection. As the S7 connection is set, you need to permit access with put-get communication from remote partner. Mark the S7-1500 CPU. In the General tab, under Protection and Security, Connection Mechanisms, enable the Permit Access with Put-Get Communication from Remote Partner function. Repeat same steps with S7-1200 CPU. Configuration is set, compile, and save project. Load it to the both CPUs. Configurations of both CPUs has been successfully sent to the corresponding CPUs. Let's try to test if S7 connection is established. To test the connection, both CPUs must be online. As you can see, active connection is established, so passive connection is established as well. As you remember at the beginning of the video, I have briefly went through the theory. And there, I did talk, that configured connection establishment with partner is automatic, and it starts when starting up the communication capable module. Now I will try to create a hardware interrupt, by simply plugging out the Ethernet cable. As you can see, connection to the S7-1200 CPU is lost. S7 connection is also disconnected. An OS of the CPU tries to reconnect it automatically. I have been talking about that in the theory part of this video. Now I will try to connect the Ethernet cable back to the port of the S7-1200 CPU. After interruption, S7-1200 CPU is back online, and operating system automatically re-establishes the connection without intervention of the user. Connection resources are reassigned. S7 connection is back online. It's time to write a user program for data exchange. User program is divided into two parts. First one is a user program of the active CPU, and second one is user program of passive CPU. Let's start creating user program of active CPU. I have created 3 PLC data types for put, get, and error evaluation. Now let's create a data block with general data. The data block for general data is finished. It contains parameters and error status of the put and get functions. Next step is to create a data block that stores values of local and remote partner. The data block must be non-optimized, so you need to deactivate optimize block access in data blocks properties, attributes. Open up OB1, find put function in the communication library, S7 communication. Drag and drop it onto network 1. Assign connection from configured connections. In this case it will be active connection. By assigning connection, parameter ID is set automatically. Assign tags from global data block to other parameters of the put function. As ID is assigned automatically, you can leave it like that, or assign tag from global data block. Parameter SD1 is a pointer to the local data area. Parameter address 1 is a pointer to the data area of the remote partner. Next I will evaluate the status of the job. If the error occur, the execution request will be terminated and the error value will be saved to the global data block. Same way will be done for successful execution of the job. The execution request is terminated, and status is saved in the global data block. Put function is finished. Find the get function in the same library, drag and drop it onto OB1. Assign connection the same way as I did for put function. Assign corresponding tags as function parameters. Evaluation of the job status is realized same way as for put function. User program for active CPU is finished. You can compile, save, and download it to the CPU. Next step is to create a user program for passive CPU. The program for passive CPU is similar to the one that I have already created active CPU. The only difference, instead of active connection, you will select passive connection. Programming side is done, let's test the created application. To test the application I have created two status tables. One for active CPU and another one for passive CPU. First I will assign some values to the tags. Now I will try to write data to the passive CPU, using put function on the active CPU. As you can see, data has been written successfully. Remote values on the passive CPU have changed according to the values on the active CPU. Now I will try to get data from the passive CPU. Retrieval was successful, as remote data values on the active CPU have changed according to the values on the passive CPU. Now I will try same commands, but on passive CPU. As you can see, data exchange is successful. The main goals are achieved. Connection and data exchange is successful. If you find this video useful, please like it, and subscribe to the channel. Thank you for watching and happy coding.